Well, welcome everyone. Good afternoon. And my name is Amol. I work for a company called Qualys, which is based in California. But actually, it was founded by a few French engineers in Paris a few years ago. So before flying here to Paris, I was practicing my French with a couple of people at my work who speak French, and they told me that I need more practice, which was a very polite way of saying that don't do it. So I will take their recommendation and do the presentation in English. So in the next hour or so, we'll talk about SCADA security. I was chatting with some folks at the coffee break earlier this morning, and what's sort of getting their expectation from conferences like these, and especially from my presentation. Some folks were really excited to hear that there would be like packet dumps, network sniffs, and things like that on the slides, while some people wanted more of a global view of what's happening in the SCADA industry and in that space. So what I'll try to do is try to get the best of both the worlds and try to please both the audience. So what we'll do in the next 50 minutes or so is we'll go over some of the SCADA basics, just to make sure that all of us are talking about the same thing. We'll look at the threats. We'll look at where are these threats in SCADA systems, why these threats exist, and how can they be exploited. We'll also go and look at some of the challenges. So if we know where the threats are, we know how they can be exploited, what are the challenges, why can't we fix them, why can't we patch them. And finally, some recommendations and proposals to secure SCADA environments. And yeah, last but not least is I'll introduce you to a free open source tool that I created to sort of audit your SCADA network. So we have quite a bit on our plate. Let's get started. So this the SCADA security happened or came in my life about 6-7 years ago, when one day my boss comes to my desk and asks, "Hey Amol, do we have signatures to identify SCADA vulnerabilities?" Now, to give you a bit of a background, what my team does is my team writes vulnerability signatures to identify threats, misconfigurations, vulnerabilities, any way in which an hacker or attacker could get into a network. At that time, I knew what SCADA systems were, but we were not ready to write vulnerability detection signatures for SCADA systems. So I told my boss that, hey, give me a few days or a few weeks, and we will see what we can do. As I started talking to people in the industry, I found out that there is a lot of differences of opinion in what actually a SCADA system is. Some person says that, no, this is not a SCADA system, this is an industrial control system. Some person says, oh no, this is not an industrial control system, this is a distributed control system. Some person says this is a SCADA system. And there are a lot of differences in these different terminologies. But for the sake of this presentation, I'll use the word SCADA pretty interchangeably. So although there are some differences, I think for this presentation, the word SCADA works. So what are some of the pictures that come to your mind when someone says SCADA? What is the example SCADA system? And I would like to make this talk a little bit interactive, so feel free to stop me anytime, say, hey, I don't agree with this, or I have seen something different, or this is bogus, or explain it again. So some of the pictures that came to my mind at that time were these electrical power towers which carry electricity. gas and oil pipeline, windmills. These are all example of SCADA systems. And the ones at the bottom, they are more or less called as industrial control systems, which is basically food manufacturing or automated. The example that I have is donut manufacturing or car manufacturing. So the difference between the systems on the top is the general rule of thumb that I use is if you sort of hug a SCADA system, and if you end up hugging half of a country or even half of a continent, like the ones in the pictures above, it's a good chance that it's a SCADA system. While those at the bottom, they are huge. They can span one factory or multiple factories, but they are still not as distributed as the ones above. They are usually referred to as industrial control systems. So there is a difference between these, but as I said, for the sake of this presentation, we will use we'll use the word SCADA interchangeably. So SCADA stands for Supervisory Control and Data Acquisition. So what usually we do when we have a problem of writing a signature to identify vulnerabilities in a vulnerability scanner is that we basically get the system in our lab, we bang on it till it breaks, and then basically write signatures. Or if there are any existing vulnerabilities that are known in that system, then it's easy. There are already exploits available. We just have to write signatures for those. But that was difficult for these systems, as it was very difficult to get a handle or to get our hands on these systems. And also there was a question of why do we really need signatures for these type of systems? So I was investigating a bit more and found that there have been a couple of accidents in SCADA systems, and the links that I have are some of the US government links for liquid pipeline failures. That's the ntsb.gov link, which details what happened if it was a manual error, if it was a machine error. Examples of power failures, and there have been a lot of accidents generally around SCADA systems. I started to look at more such incidences, and there have been cases of vandalism too. By the way, at the end of this presentation, I'll give you a link where you can access this presentation, so you don't have to write these links down. And the example here I have is of a power company in Portland, in the United States, where some vandals, they destroyed some rubber gaskets on electrical distribution lines. And although it did not cause a major power failure, the electrical company still had to reroute power. They had to send crew in to fix that issue, and so on and so forth. So it did cost a bit of headache and money. There have been cases of insider threats, cases like disgruntled employees. And the example that I have here is the one from Australia, where someone was fired from a water treatment plant, a sewage treatment plant. And what does he do the next day? The very next day, he, from the parking lot of his company, he wirelessly, because he knew all the schematics of the systems, all the blueprints of the systems, the guy goes and opens the sewage into rivers and parks in Australia. Did cause a lot of embarrassment to the water company as well as generally to the country as well, because it was a highly publicized incident. But what we didn't recognize at that time, and what people have been talking in this conference a lot, is the threat of APT, which is basically advanced persistent threats. Threats that most probably use 0 days, which are not known even to the vendors. Threats that are not really focused on stealing money or credit card information, things like that, but usually have some states behind them. And the example here is of the Dooku worm, although that is a little bit outdated now. Who can give me a few good examples of such SCADA-related APT attacks, real world? Stuxnet. So Stuxnet was the first. I think in the panel discussion, there was a brief mention of this incident. Stuxnet was a virus which affected nuclear power plants of a certain country. Then there was this Dooku virus, and this link is actually from Symantec. They concluded by reversing the virus that it was written by the same people that wrote Stuxnet. And something more recent. Has anything more recent happened? Flame, yeah. So there was a magazine out there, Windows something. I couldn't read it because it was in French, but it had flames, and I'm pretty sure it had details about the flamer or flames virus. So if you want to know more, just Google it or just grab that magazine on your way out. So needless to say, there is an urgent need to secure these type of SCADA systems. And at that time, I mentioned to you a while ago, this was about 5 to 6 years ago, when we were tasked to write signatures, vulnerability signatures, to identify vulnerabilities. We didn't have access to any of industrial control systems or these huge, diverse SCADA systems. So what we did instead was that for our own engineers to understand a SCADA system better, we created sort of a framework that we use internally to understand these systems, and which enabled us later to write signatures. What you have on the left-hand side, this is the field. This is basically, it could be thousands and thousands of kilometers away from your control center. And on the right side, what you have is the control center, where there are operators manned 24/7 in a control center to monitor the activity of the SCADA system. So let's take a little bit of a detailed look at this. On the extreme left, in the field, what you have are the sensors, meters, and field devices. These are devices like the ones here, which are, this is a temperature sensor. The next one is a pressure sensor. Oh no, I'm sorry, the first one is a photo sensor. It basically just tells you if there is light around it. The second one is a pressure sensor. The third one is a temperature sensor. So what they do, these sensors, meters, and field devices, is that they capture parameters in their environment and convert them into analog signals. Pretty simple and straightforward. What they have is they have a two-way communication with the next device that the next block that we put in our framework. These are data conversion. This is a data conversion block. So the first one is acquisition, where you acquire data. The second one is data conversion. And these contains PLCs, IEDs, RTUs, or programmable logic controllers, intelligent electronic devices, or remote terminal units. And what they do is they convert this analog signal that they have received from the data acquisition component from the field and convert it into digital information. And just to give you an example of how big they are or the size, you can see a man there. He's holding a PLC, which is most probably attached to, I don't know, some sort of either electric pole or a windmill pole or something like that. They are this size. So in this framework of SCADA system, number one component, data acquisition, where you acquire data. Two-way communication with data conversion, which converts it to digital form. And then this data then gets communicated to the last box using one or more of these communication protocols. So this communication could be a wired communication, it could be wireless communication, it can happen over Ethernet, and it uses one of the dozens and dozens of SCADA protocols that are available. So I read somewhere on the internet that there are about 100 SCADA protocols, and I don't know 100 SCADA protocols, but I easily know about 24 of them. So there are a lot of open source, closed source, proprietary, type of protocols that are used to transmit this data to the last component, which is data presentation and control. This is where I said there are operators manned 24/7, which are looking at alarms, reacting to them, and it looks something like this or this or this. This is also called as HMI, or human machine interface, because it's the interface for the humans in the system. So this is pretty much the basics part. Everyone pretty okay with this? Any questions about this? Okay, good. So where are the threats? We saw that we have these field devices out there. We have data acquisition, data conversion, communication, and command and control. We studied some of the threats which could happen between these two components, but most probably they require physical access. Field equipment, which is basically the sensors, meters, or field devices, they generally do not contain process knowledge. And you can get information like valve 18B is open or breaker 9C is closed, depending on what type of SCADA system it is. It could be industrial control system, manufacturing automobiles, it could be electric power lines, whatever that SCADA system may be. And doing something here without process knowledge usually causes just a nuisance disruption. So the example that we saw earlier in Portland that I mentioned, a couple of vandals, they just destroyed these rubber gaskets on electrical power lines and caused an outage. They weren't knowing what they were doing. They did not know what will happen if they do this. Those were just vandals. They destroyed something, and something happened. And at least I have not seen a lot of attacks currently happening in this in this sort of space. If you have seen something related to this, please let me know. So what we did was we said, okay, let's focus our attention on the next vector, which is the communication vector, which is how data gets communicated from PLCs to the master units. There are various attack vectors here. You can change if a man in the middle happens here, then you can basically manipulate the FEP output, and what would happen is that the operator, which is here, would see something different, would see that, oh, some valve or some circuit is open when it's closed, or closed when it opens, so on and so forth. In the communication area, there are, as I mentioned, a lot of proprietary, open sourced, as well as different protocols that are used. And what we decided was to look at some of the protocol threads. These are the threads that can be executed over the network, since the data is flowing over the network. It's not like this component where you have to actually physically go in the field, climb up a electric power pole or something like that to destroy something. These are communication threats, so you can, a malware can do this remotely. So we decided to look at a certain communication protocols, SCADA communication protocols, and the first one that we decided to look into was Modbus. How many people have you heard of Modbus? Okay, a couple of hands going up, so that's good. Modbus is a pretty old protocol. It's about a 35-year-old protocol. It's a pretty simple client-server protocol. And if you know any other client-server protocols like FTP or HTTP, Telnet, SSH, whatever, the basics are the same, which is the Modbus client sends a request to the Modbus server, and the Modbus server gives back the response. So it's the same. The only difference is that the client in this case is called as the master, and the server is called as the slave. So basically your client is, if I sort of go back to these pictures, this is the Modbus client here. which asks for data from the servers which are in this area. So let me get back to the slides. Great. So that's Modbus. What it consists of is it has an application data unit and a program data unit. It was not initially designed to work on TCP/IP since it's like a 35-year-old protocol, but later it was basically modified to run on TCP/IP. And the way it was modified was you just put the Modbus packet into your TCP packet. So what you have at the end of the day is an IP header, a TCP header, and the Modbus header, and all the Modbus codes. So that is how it was sort of ported on TCP/IP. So let's quickly take a little bit detailed look at this protocol to see if there are any threats at the protocol level. So let's get rid of these TCP/IP frames. Let's just look at the Modbus. What you have here is you have in the Modbus header a transaction ID, a protocol ID, length, and a unit ID. Now this may be a little overwhelming, but just stay with me for 5 minutes. The transaction ID is a pretty simple transaction ID. When the server, when the client asks the server that, hey, tell me what is the temperature or tell me what is the pressure, it uses a transaction ID saying that this is, or transaction ID or a question number, you can say. This is question number 10. Tell me temperature on what you have. And then the server responds saying that the temperature is this for your question number 10. Then my question number 11 would be, okay, now tell me what the temperature is. So it's just a unique ID to identify what request was sent, what question was asked, and a unique ID to get the response. Protocol ID is fixed for Modbus, it's 0. Length is the length of the entire packet. And unit ID is again something interesting. That is basically a client could be talking to many of the servers. So there could be many field devices. There could be many electric towers, right? Or on a single tower, there could be many units connected, top of the tower, bottom of the tower, things like that. So the client asks the server that tell me the temperature or pressure or whatever the system is connected to for unit number 1, unit number 2, unit number 10, things like that. Pretty okay till now? Yeah, go ahead. Yeah, you can only have 256 units connected to that particular server, but then there are thousands of these servers. So there could be this one server on, like say, one tower which has 256 units, and there could be thousands of these servers. Function codes are basically simple function codes telling the server to do something. So some of the examples here are read discrete input, write discrete input, read coil, write coil. It's basically the client is telling the server, hey, read, which is tell me what the temperature is or the pressure is or whatever, and write is basically close this valve, open this valve, set this unit. The protocol really doesn't, it's not concerned with if what the server is actually connected to. It could be collecting temperature, pressure, valves, it could be anything. And data is just data for that function code. So you can write a pretty simple one page Perl script that basically creates a packet. In this case, you put some transaction ID. I've chosen 256. You put a protocol ID, which is always 0. You calculate the length of the packet. Of course, here I've hard-coded it. You put a unit ID where you want to talk to. You put a function code, which I've put 3, which is, I think, read holding registers. And you put data, which registers you want to read, how many registers do you want to read. And now this is TCP/IP, Modbus on TCP/IP. So you send it over using simple TCP sockets, port 502, which is the default port, to the server. So the request looks something like this. You can see in circles that I think this is Wireshark has identified transaction ID 256, protocol ID 0, length 6, unit ID 1. Oh, and by the way, whoops. Usually when we work on some of the weird protocols, we need to sometimes write plugins for Wireshark or things like that because they don't decipher the packets correctly. But in this case, all the sniffers that we tried have a pretty good support for Modbus protocol, and we didn't have to do anything here. We just ran Firefox and it was able to capture everything correctly. The response that we get is something like this. The answer to my question, it gave 5 bytes back, 10 bytes back of response for 5 registers, 2 bytes per register. So okay, good. I sent a request. I sent a request to some unit. I asked for some values. The unit may be connected to some temperature sensing thing. It gave me back the temperature. So pretty good till now. But what is wrong in a bigger picture? Or as far as security is concerned, what is wrong here?
First thing I think, if all of this is plain text and encrypted, you could quite easily just modify it and re-inject.
Very, I mean, that's correct. That's very, very good. Anything else? No identification of the server, exactly. So basically, usually any security protocol is measured against this, right? Confidentiality, integrity, and availability. So in confidentiality is authentication and authorization. So authentication is the server should ask you to authenticate, hey, you are asking me to read a temperature reading or write a temperature reading, which is basically change the temperature. Who are you? Who are you? Give me your authentication token. So there was the client, if you saw in the Python example, the client did not authenticate or anything. It just asked it to do it. If there is no authentication, it's difficult to have authorization as in, okay, you are this an ABC person. Are you authorized to do so? Are you authorized to only read or only write? If there is no authentication, there cannot be any authorization. There was pretty easy to do any man-in-the-middle type of attacks as you described, because there was no encryption. And again, I'm not here to bash on Modbus because it was a pretty old protocol in industrial control systems, and it worked perfectly in where it was intended to work. It was intended to work in industrial control systems which were closed. So this is a system and it's not connected to anything outside. But now when it's connected, when it was ported to TCP/IP, you can know what would happen if this type of protocol runs on the network. So we said, okay, this is a pretty old protocol. Let's look at some of the newer protocols. So we decided to look at another protocol called DNP3. How many people have heard this sort of a weird name? It's a protocol that was designed from the grounds up for the electrical transmission lines because it has a lot of good things over Modbus. So what Modbus has is the client has to constantly poll, as in ask, hey, what is the temperature? What is the temperature? What is the pressure? In DNP3, you could say that, okay, give me the temperature or pressure or whatever, only if it has changed. Otherwise, I'll assume it was what it was earlier. In DNP3, a slave can, by itself, tell the client, or basically the client can register that, hey, whenever the temperature or pressure or whatever changes, notify me. So the slave can automatically, the server can automatically notify that, hey, a temperature has changed or a pressure has changed. So a little bit more advanced than Modbus. And oh, I forgot. So this is a screenshot from the open source tool that I mentioned a while ago. What it is doing is it's running in the Modbus mode with the -m option. And again, at the end of the presentation, I'll give you links where you can download this and try using this. So what it is doing is it's trying to brute force some of the Modbus unit IDs. So we said, okay, DNP3, it's a newer protocol designed from the ground up. It has these 3 layers, and again, we are not going to go into a lot of details about this, but it has a link layer, a transport layer, application layer. And the application frame looks like this. Again, not going into too much details, but it looks sort of similar. You have some request, and then you have some response. The request has some function codes, pretty similar to Modbus, like read, write, give me a setting, read a setting or write a setting. This is the transport layer frame, which provides a little bit transport type of functionality. And this is at the bottommost layer, a link layer frame, which has a start byte, length of the packet. It has a few function codes, destination, source, and now we have some sort of a CRC here. So a little bit improvement on Modbus. So again, a simple Perl example, which creates the packet, fills in your buffer, and this example again is from the SCADA scan tool that I mentioned to you, that you can download at the end. Source address, destination address, CRC. This is for presentation, so I have hard-coded the CRC, but I mean in reality you would calculate it, and you send away your packet on the TCP port. What you see is a Modbus request, and again, Wireshark or many of these sniffers, they already have protocol decoders for a lot of SCADA protocols. So again, in this case, we didn't write any custom plugins for Wireshark. You send in your request, you see the request going. This is basically a request of the data link layer to just get the status of the line. What's the status of the line? You get a response with several bits saying, and each of these bits would correspond to something in that environment. Again, we asked the same question. Well, this time all of you should know what is wrong, right? Yes, no? Well, same thing. Confidentiality, integrity, availability. Did it provide any confidentiality? No. The client sent a request, the server just acknowledged it and obeyed what the client was trying to say. Same thing with integrity and availability. And this is again a screenshot of the tool that I mentioned running in DNP3 mode. But again, all is not lost. It's not all doom and gloom. What DNP3 did was in 2007, they came up with a newer specification of this protocol, which has many of the functions that you said. It has hashing and cryptography and a lot of these things that newer protocols support. So if you use a secure DNP3, which is a newer version of that protocol, I think you are pretty much in good hands. So we looked at the physical threats into these SCADA systems, communication threats. Did find a lot of communication threats. What we ended up doing was, if our scanner finds Modbus running or DNP3 running, we would say that, hey, you are vulnerable. I mean, you are running protocols which are not secure inherently. So make sure that you have other security processes in your network to sort of compensate for that. So lastly, we focused attention on this last component. This is the control component, where, as I mentioned, there are operators manned 24/7 in a manufacturing plant or in any sort of plant to look at what's happening in the system. And the number one threat that we found in this area is that the control system network is connected to the corporate network, or sometimes even to the internet. It used to be that these networks were air-gapped, but more and more what we are seeing is that this control system network, which is heavily, most of the time it is pretty heavily secured in a physical way. So to get into this control system, There is usually like a guard or something standing. You need someone who has authorization, whose fingerprints or some sort of a biometric thing works to get inside the room, which has the command and control. But now all that physical security, I think, is of very less use because these networks are connected to the corporate network. So your control system network is connected to the reception network, to the HR network, to the network that you sign in the lobby, and so on and so forth. So viruses and worms, they can easily jump from your internal network, from your HR network, from the receptionist into this network. In some cases, we also found these networks are even connected to the internet. So to give you an example, after Stuxnet was a big deal, there is a service called as Shodan, SHODAN. How many of you sort of use this service? Okay, a lot of hands going up. So this is basically a scanner that scans the internet and in its database saves the IP address and the banner. So if you're running SSH Telnet, it will save the Telnet banner. If you're running an HTTP web server, it will store Apache or the whatever banner that the service gives. So after Stuxnet was a big deal when I went to Shodan, and it also shows the top queries. So I went to Shodan and I looked for the top queries, and people were already searching for Siemens, PLCs. I mean, all of you know, right? Like Stuxnet used or targeted the Siemens PLC, programmable logic controllers. So I said, okay, let me type my own search. So I typed my own search for looking for SCADA systems, live SCADA systems on the internet. And sure enough, I found a couple of hits there. When asked to a lot of people why they have SCADA systems connected to the corporate network, usually the answer is ease of use. So there is some director or big manager in the SCADA network who wants internet access. And the easiest way for them to do that is, instead of giving him a different machine which is connected to a different network, they just connected their SCADA network to their corporate network. For SCADA systems connected to the internet, which is the entire world, I don't know, can you guess why would anyone connect their SCADA system, which is very critical, or an industrial control system, to the internet? Remote access, yes, that's right. That was the number one reason why they are connected to the internet, to get remote access. In one case, what we saw was the company wanted to give their clients, their customers, information about power outage and things like that. So instead of having the data transferred from the SCADA system securely to some place where it can be accessed, they just connected the SCADA system to the internet, because now they say, no, okay, now our customers can see on a web page of their SCADA systems what's happening. So there are various reasons. No authentication or per user authentication. So when you go inside this facility which has command and control, there are a lot of machines with big displays that shows what's happening in the SCADA network. But then there itself, there is no authentication. If you are inside, you can just run there and type anything. Of course, there is no physical security threat, as physically you cannot get in there. But as I mentioned, if this network is connected to the corporate network or to the internet, viruses and malware can jump from your corporate network into these systems, and they can manipulate the HMI or human machine interface directly. There were shared passwords or default passwords. So if a virus like Stuxnet can identify that you are running a Siemens PLC, then it's very easy to go on vendor's website, read the documentation, see what the default password is, and basically try that as your first guess if the malware is trying to brute force passwords. And no password change policy, which is basically you know what the password change policy is. So when asked why they don't have passwords, the number one response that I received was that these are critical systems. If there is, for example, a fire in the plant or something like that, they don't want operators to go type in the password, oops, wrong password, type in again, wrong password. things like that, because they have to respond immediately. That is okay, but in one of the SCADA conferences that I was talking at, there was a person from the military, and he said that, well, we have 18-year-old people who type in 25 character long passwords which are changed every 2 weeks, and they never miss it. Now I know in the military you can enforce a lot of things which you cannot in private sector or in these type of systems. But I think if we are dealing with critical infrastructure, it's high time that we start regarding these systems as military grade systems. No patching. So this is a long subject when it comes to SCADA. It used to be that a lot of these SCADA systems were proprietary, but in the 90s, the SCADA owners, they told their vendors, which is basically ABB, Rockwell, all the SCADA vendors, that can you port your system on Windows, because it's a lot cheaper. It's a lot cheaper to have a system on an x86 machine running Windows than having like a totally proprietary thing. And the vendors, they did that. For them, it was cheaper as well. It's easy to find Windows developers than some proprietary sort of thing. And that was fine too, but what happened was all the malware, like we saw the PE header presentation, there is so much complexity in Windows. All the malware and worms that affect Windows now can affect your SCADA system. On top of that, patching becomes a big headache. Microsoft releases patches every patch Tuesday, every month, at least a dozen patches every patch Tuesday. And as if I am a SCADA system administrator, what am I supposed to do? Am I supposed to just apply these patches blindly without knowing that this could cause something bad to my SCADA system? The SCADA vendors really don't have, or every patch Tuesday, they don't give any guidance to the SCADA administrators that, okay, we have tested this patch, apply this patch, and your SCADA software would be fine. There is no guidance like that. So if I'm a SCADA administrator, if Microsoft releases a patch, if my SCADA software vendor doesn't give me any guidance on what to do with it, I won't apply the patch, because the patch could cause something wrong with the working of the SCADA software, causing like power disruption or something that is really bad. And as a result, none of these systems are patched forever. I mean, we have seen systems that are totally unpatched. Windows XP, Windows NT, a lot of older systems which have absolutely zero patches, and now they are connected to the internet. So you can just imagine internet or intranet, what could happen if a Windows system which is not patched for like 5 years is connected to the internet. There are some systems which are even not restarted for years, and when we ask like why are your systems not restarted, the simple answer is that they are not confident that after the restart or the reboot the system will even come up. We found that a little bit funny, but that is the stage at which a lot of SCADA systems are running old off-the-shelf software, Windows NT or Solaris, really older versions, and that are not patched. And now, since this type of proprietary system has been ported to off-the-shelf Solaris or Windows or Linux systems, all the problems that are affecting your normal off-the-shelf operating systems affect these systems. Like there are unnecessary services that are running and whatnot. So to conclude, some of the challenges, and I think the biggest challenge to SCADA system is the long life cycle. If all these problems were in my laptop, fine, in 1 year I will replace the laptop, because 2 years, the life of the laptop is 2 years, 3 years. But SCADA systems are meant to last for decades or multiple decades. They are meant to last for like 50 years or 40 years, depending on what the application is. And it's very costly to upgrade part of the system and forget about upgrading the entire system. Another thing is that there is no, we already mentioned, no testing or guidance on OS level patches from SCADA vendors. some systems are managed directly by the vendors. So we went into one of such installation, and the SCADA owners said, "This is a Windows system. So do you want to audit it?" And we said, "Yeah, we have seen a lot of Windows systems. What's the administrative password?" And they didn't have the password. That's because the systems are directly managed by the vendor. So it's difficult to perform audit or a pen test, not really a pen test, but audit without causing any harm to the system. There are a lot of other machines on this SCADA network, which are basically data historians, which is the databases, web servers, and things like that, which are also, since they are off-the-shelf systems, these are also affected by all the flaws that we just saw. There are a lot of internal differences between people who manage SCADA systems and their typical IT network, IT system administrators. So what happens is that in a company A, someone tells a system administrator, "Oh, we have SCADA system, make sure it's secure." The system administrator goes and just blindly runs some scanning tool on it, which causes these PLCs, which are really very fragile, to just fall down. And that causes a lot of tension, and what happens is they say that, okay, we are never going to scan our SCADA systems after that. And this has happened in almost all instances that we know of. And this is something that I brought out because if you are using any tool, even the tool that I am going to show you, please use it very cautiously. In any factory or in any sort of installation, every quarter there is always a downtime. Use it initially there. Ask your vendor, if you are using a vendor's tool, have they tested the tool with the protocols, with the PLCs, and with the hardware that you have. So really push the vendor, since you are paying them for these tools, make sure that they have already tested it against in your network. Some of the proposals since a lot of these SCADA systems are more and more looking like normal IT systems, you should have all the best practices that affect the IT systems: strategy for password policy, access control, access roles, strategy for software upgrades and patching. Try to have a SCADA test environment. This is easy to say, difficult to do, because it's very expensive to have even a small part of your system as a test system. And demand from your SCADA vendors that they expeditiously test patches and approve them. In some cases, it's even worse. When Microsoft releases a patch, the SCADA vendor then recompiles the patch, and that is the patch that you can apply on your SCADA system. So there is a lot of time lag, which gives precious time to hackers and attackers to basically compromise systems. Make sure that your SCADA vendor gives you newer protocols, as we saw in case of DNP3 and Modbus. There are newer secure protocols available, so make sure that your software has those, and also make sure that your administrators are using those protocols. So it's not just that your software supports secure DNP3, but it also has to be enabled. And generally apply your experience from your IT or network management and security background to the SCADA network, because more and more your SCADA network is looking as your like the normal network. Auditing and scanning will also go a long way. So this is basically the SCADA scan tool that I was talking about. It's currently even pre-beta, I call it alpha version. It scans a network range, works on TCP/IP, uses or identifies Modbus, DNP3. But the fun will start like a few months down the road, when it will start supporting SCADA master vulnerabilities, SNMP support. And in the final release, what we plan to do is have user configurable signatures, because no matter how many SCADA systems that I or we look at, there will always be a SCADA system that we don't know of. So if a user can upload their own signatures, then I think that will generally help the community and everyone. So this is a open source tool, open source, free. Use it carefully. If it crashes something, please do not contact me, because if you run it against some of these older PLCs, it will crash. and the link to download it is on the top of the page. I frequently post updates on the tool, on the newer things that are implemented in the tool on the Twitter profile, so if you can get updates from there. And finally, the last link is some links to SCADA blogs and things that could help you help you in securing your SCADA network. So, any questions? No? Well, no questions is... Oh, great.
Have you ever tried to scan over protocols for example, even like TCP support?
Sorry, I didn't get the question.
I mean, you spoke about the Modbus and the TNP3 protocols, but have you implemented some other protocols?
Oh, some other protocols. So,
I'm thinking about the Pi, for instance.
so yes. So currently, the tool at least supports DNP3 and Modbus, which are the communication protocols. Our plan was to support more communication protocols, but what we are finding in real life is attackers are. I mean, there are a lot more easy ways to attack a SCADA system, rather because if I write a malware to basically break the protocol, it still becomes a little complex. People are using pretty easy techniques which are a vulnerability in the web server of the SCADA system, or a which is no different than any Apache or web application vulnerability, or vulnerabilities in the SNMP implementation of the SCADA system. So attackers are using a lot easier ways than to attack the protocol. So we are focusing a little bit more of attention on and writing signatures for those type of attacks. But you can mail us some of the protocols that you are interested in, or you can mail me, and we can give it a shot.
Do you use your tool on the board internet and find some big information for SCADA devices?
So we have not used.
Find something interesting.
We have found a lot of interesting stuff. I don't think I can share all of it here, but what I can do is just go to Shodan. I think you all know what Shodan is. If you are interested in, like, say, or if you have a Siemens PLC, just go to the manual, see if it runs Telnet, if it runs a web server, what the banner is, and just check for that banner on Shodan. So you don't need to use any of my tool in any good or bad hacking that you want to do. You can you can do I think pretty much all by yourself.